Hey, hello everyone. Let me share the screen and we shall get started in the next 1 minute.
Become an industry-oriented full.
Okay, I'm just checking on whether we are YouTube live or not. I don't think we are YouTube live yet. So let me check with the concerned person. Just give me a minute while I ensure that it becomes YouTube live. All right, so we shall get started. Let's go here and let us understand more about this. um, we have, oh, why did I click on webinars? My bad, sorry. Mind map. If you go to mind map, which is there on the menu and drop down on AI and deep learning, you will find AI and deep learning here. And we discussed about understanding the business problem, recording the objectives and constraints, collecting the data, cleansing the data, performing data mining or and machine learning, evaluating. All these things were discussed. And we have also discussed about deep learning primer and mathematical foundations also to some extent was discussed. And then we got into the artificial neural network concept here. And let me go copy the code pertaining to ANN and paste it here. And let me explain in detail on what was discussed yesterday. Python programming is extensively used, and actually, if you ask me, this is a de facto tool when it comes to AI and deep learning. Once again, just to demystify a few things, AI is application that you build using data science concepts. Within data science, you have data mining. Within data mining, you have machine learning. Within machine learning, you have deep learning. And within deep learning, there is a new field called as reinforcement learning, which is catching the attention of the world. We have Numpy, which is used for numerical calculations, SciPy, which is used for scientific calculations, Pandas, which is used for data manipulation purpose, scikit-learn or sklearn, which is used for machine learning libraries, handling machine learning concepts. Then you have something called as stats models, which is used for statistical analysis. Then you have matplotlib for data visualization purpose. We have Seaborn, which is used for advanced data visualization purpose. We have TensorFlow, which is used for deep learning. Keras is also deep learning, and we have PyTorch. These three are used for deep learning purpose. And we shall be discussing about deep learning. Here we also need alongside a few other libraries, and we are looking into that. Import Numpy as NP from Keras models, import sequential. The moment you do that, it says backend is TensorFlow. And do you know what? In the latest of the version, TensorFlow version 2 onwards, when you want to refer to Keras, you have to say TensorFlow.Keras. TensorFlow.Keras. This is how you need to give for a certain things. For a certain other things, it's not needed. So we discuss these things. Anything which is written after hash is not needed. That means it's a comment. Okay, if you don't want any line to move ahead, you can just comment it out, right? And then we have yesterday imported pandas, and we have read the file, right? The training data set and test data set, which is MNIST handwritten digits. And these handwritten digits have a dimension of 28 by 28, which is 784 in total. So you have 785. You might ask me, hey, where did that additional um, one number come from? It's showing as it's 785 and not 784. This additional one is an output variable, which has a label 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 10 class problem because numbers can be 0 or 1 or 2 or 3 or 4 or 5 or any of those. And if you have a handwritten check wherein someone has written $5,689, it should actually read it exactly right. Accuracy should be almost 100%. It cannot actually be 100%, but it'll be almost 100%. Only then what, what in Western world, if you go to ATM in a few of the states, you just need to scan your check here. Okay, you'll have check scanner and it will scan and dispense the money for you. You can just take the money and walk away. As opposed to going and depositing this in a bank, people in bank, checking whether that's the right number, that's the right signature or not. Everything is to a great extent automated. Okay, and the next thing is data pre-processing. First step here is you imported the required libraries. So I would put it here. Import required libraries. This is step number 1. Step number 2 is import the data or the data set. So you loaded the data sets here and you stored those in train and test. What is the third step? Data pre-processing. As part of data pre-processing, you're taking all of your inputs and converting them into a float format. We discussed in yesterday's video on why we do that. Okay, and we are also, yesterday we have also done another thing, which is after this, we have normalized the data into the range of 0 to 1. I would strongly recommend you all to watch yesterday's video, which is day 6, if you find any disconnect, because after day 6, we are moving to day 7. And here, there is a function called as numpy underscore utilities to categorical. So what happens is, let me first go to y underscore train Where is this y underscore train? It's here. You have all those zeros, ones, twos, threes, all of those, right? So it's a 10 class problem. So when you say two categorical, it actually does a one hot encoding. What do you mean by one hot encoding? It will convert these numbers in this way: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 in that way. Since this row here has 2, you'll have a 1 here and 0 everywhere else. And here it's 2, so you'll have a 1 and 0 everywhere else in that way. Okay, so you have 1 against 2 and 0 everywhere else. So you're converting that to categorical. Both training and test data is converted to categorical. Now what you're doing is you're going to this y test. Here, if you observe, this y underscore train, y underscore test, say y underscore test, dot shape. Dot shape will give you the rows and columns. This is rows and this is columns. And you have 1000, which is also expressed using an index number 0. This next part is expressed using an index number 10. Sorry, index number 1. This 10 is expressed using index number 1. When you say y underscore test dot shape of 1, you're referring to this 10. And you're using assignment operator equal to, you're storing that in an object called number of classes. Okay, so this did not run. Yeah, now. So you have this number of classes which has a value 10. Okay, because we had 10 here. You can look at the shape x underscore train dot shape. When you do that, you know that there are 5000 rows and 10 columns. Why 10 columns? One hot encoding. You'll have 0, 1, 2, handwritten digits could be any of these, right? Handwritten digits could be any of these. Okay, and when you say train dot shape, you have all of these, which are appearing in 10 different columns. And this will get translated into 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And for each and every row, you have 5000 rows. In each and every row, you'll have a number. Against that number, you'll put a 1, rest all will be zeros. That is one hot encoding. Okay. Same is the case with x underscore test dot shape. You have 1000 rows and 784 columns. And y underscore test also has the data, 1000 rows and 10 columns. Then we are defining a function. Okay, we are defining a specific function called design underscore MLP. MLP, I mean, you can give any name for that case. Why are we giving it as MLP? Because it is kind of multi-layered perceptron, right? Artificial neural network or multi-layered perceptron, just to get that context. Okay, we are giving that. Okay, just a minute, sorry. Yep. So here we have defined a function. Whenever you want to define a function, you always start with definition kind of, right? And then you give an indentation. Indentation means give a space. By pressing tab on your keyboard, there is a function or there is a key called as tab. When you press that, it will move in that way. Okay, here we are defining a sequential model. And here what we are doing is we are defining the input dimension to be 784. So 1, 2, 3, 4 in that way. How many would you have? You'd have 784 neurons in the input layer. You're connecting that to 150 neurons and dense means fully connected. So you have 150 here. These 150 are connected to, and for all these 120 neurons, the activation function that you're going to use is ReLU, rectified linear unit. Then you're connecting that to another 200 neurons. Okay. And activation function is tanh, hyperbolic tangent. And you're then connecting that to another 100. And then you're connecting that to another 500. And tanh is the activation function. Finally, you're closing it with number of classes. Number of classes, we already have 10. So finally, you will have 10 neurons. And you close it. And you're using activation function softmax. I'm not sure whether you still remember, right? But then if you have your output layer, which has more than 2 neurons, more than 2 classes, then you use softmax. What is the role of softmax? It will just ensure that it takes the numbers and converts that into probability values. That's the only purpose. So from here until here, it is called as model definition. You define your model. We define the model. After you define the model, what we do here is we compile the model. And when you compile the model, we are giving a loss function as categorical cross entropy, optimizer as Adam. There are a lot of optimizers, right? We have discussed about stochastic gradient descent, batch gradient descent, and mini batch SGD. And within mini batch SGD, there are a lot of variants such as ADA grad, ADA delta, RMS prop, Adam, so on and so forth. So you're using that. These are all variants of mini batch SGD. And you're using a metric for evaluating your model. Remember, when you have more than 2 classes, then you'll have a loss function which is categorical cross entropy. Okay, and then you're saying return the model. That's I mean you end it basically. And you're storing all these in this function called as design underscore MLP. You're storing in that. Now, let me run this portion. Done. Now what we are going to do is we are going to take that design underscore MLP and store it in model. Let me run it. Done. Okay, we are storing that in model. Now when you say model.fit, you want to run the model. So there are multiple steps which have happened. Okay, let me repeat that once again. So what we have first done is, let me also, okay, put it this way so that we have ample space to clearly write down. Number one, import the required libraries. That's one thing that we have done by importing. Second thing is import the data set. That's done. Then data cleansing, third part is perform data cleansing. Then once you perform data cleansing, what do? This is all data cleansing or data pre-processing basically. And then what did we do? We first defined the model. So fourth step is model building. Within model building, when it comes to deep learning, there are multiple steps. Step number one is define the model. And once you define the model, the next step is compile the model. And once you compile the model, you fit the model. So when you fit the model, you're giving X and Y. Okay, X and Y is needed when you want to run the model. What would happen here when you say model.fit? The patterns between Y and X are established. And you're giving a mini batch size of 1000 and you're giving epochs as 20. We have discussed all these things. Now I think you'll start appreciating. Oh yeah, we discussed about loss function. We discussed about model evaluation techniques, how to measure the accuracy basically, right? And when do we use categorical cross entropy? When do we use binary cross entropy? Okay, what do we mean by optimizers? What is batch size? What is epoch? Now I'm sure you will appreciate all these things that we have learned. A lot of them jump into action, thereby getting confused to a great extent, right? So now if I were to run this model.fit, it started running. Wow, it finished pretty fast. So you're training on 5,000 samples. That's your training data basically. Epoch 1 of 20. Okay, in this first epoch, you have 5,000 observations. And the loss function is 1.9977. Loss, categorical cross entropy. Okay, and the accuracy is 0.40 when the weights were initially initialized. And then accuracy improved to 0.7738. Slowly and steadily, step after step, accuracy started improving. And you know what? Here it reached 0.9970. Okay, it reached an accuracy of 0.9970. And is this good? Or sure, it is good. Okay, sure, it's very good. But then you always have to check whether your model is overfitting or not. You have to do this variance bias trade-off. That is what they call it as. We need to perform variance bias trade-off. So in order to perform this variance bias trade-off, you have to test your model on the test data. So you fit your model. Now you're testing your model, evaluating your model on the test data. So you're giving the test input and output. And verbose equal to 1, what does that mean? I'll let you know. And then we are storing the results in this. So let me run it. Okay. So verbose equal to 1 means it will show you this progress bar. This is progress bar. All these equal to signs, that symbols that you're seeing here, this is a progress bar. That means the model started executing, and then finally you have a result in that way. So the test accuracy happens to be 0.94. If I were to just select this portion, evaluate underscore score underscore test, and run it, you get to see the result wherein you have the loss and you have the accuracy. Now, when it comes to indexing, this is index number 0 and this is index number 1. So what we are doing here is we are saying print the accuracy. When you print the accuracy, you want the percentage dot 3-point floating. That means floating means decimals. Here anyways you have only 3 digits. Of course you have 4 digits, but then you want to pick up only the 3 digits. That's what it means. And what do you want to print? You want to print index number 1, which is the accuracy. And when you multiply this with 100, you get this in percentage terms, which will be 94.3%. Okay, I ran it. It's 94.3000. And then when you do when you do this model.evaluate of training data x and y, and verbose equal to 0. See, from verbose equal to 1, I'm changing it to 0. Let's see what happens if we run it in this fashion. It's a silent execution. You don't see any result, right? Any progress bar, nothing. If I change it to 2, verbose equal to 2, you get to see the result that loss is so much and accuracy is 0.9980. Okay, and what are you saying here? Go to this evaluate underscore score underscore train of 1. Okay, because when you look at this train, only this portion, it will have two values. One is the categorical cross entropy, another is your accuracy. Okay, and if I run this, what it does is percentage dot 3-point floating, only 3 floating numbers, and of what? Of you go to this evaluate underscore score underscore train of this is 0, of this is 1, this is 0.998 into 100, which is 99.8. And just because you want 3 floating point values, it's showing 3. So train accuracy is 99.8%, and your test accuracy happens to be 94.3. Are these accuracy values high? Oh, sure, they are very high. Are they close to each other? Of course, they are close to each other. There is no huge difference, such as this is 99 and this is 84. No, it's almost, I mean, 5% is acceptable, but this is subjective. The percentage, how close is close, might be a question. It is very, very subjective in nature. Do we have a thumb rule? You can take 5 to 8%. I mean, if the difference is in between 5 to 8%, then you can say that, okay, it's a right fit model. Okay, and then we also have this, right? So if the training accuracy is high and if the test accuracy is low, then it is called as overfitting. It is called as overfitting or variance. If the training accuracy is low and if the test accuracy is also low, then you call this as underfitting. Or bias. Okay, if both training accuracy and test accuracy are close to each other and high, then you call that as right fit. Okay, now this is the first multi-layered perceptron or artificial neural network that we have run. Let me quickly traverse to this and then look at. All right, wonderful. I think we are game. We are good. Now we will move on to the next concept of AI. Is this AI and this, or is it AI and this? Yep. So we need to now discuss about certain challenges and practical issues that exist. Okay, let me quickly see challenges. No, this is not needed. We will get into practical issues. And by the way, I mean, I should tell this that, do you know what? We have initiated an initiative basically. This is our YouTube channel wherein from 12 p.m. to 5 p.m. from Monday until Saturday, people can join our YouTube channel live and ask their questions live. And there will be a lot of senior trainers joining in to clarify the doubts basically. And 1 second, sorry. 1 second. That's my kid. 1 second, sorry. Yeah, so sorry about that. Yeah. So from Monday to Saturday, from 12 p.m. to 5 p.m., anyone can join in. You can just pass on this message to your students also. They are free to connect and then, yeah, they can get their doubts clarified. All right, next. Um, yes. Let us get into the practical issues now. What are the practical issues? Overfitting. If your model overfits, how do I handle this overfitting problem? Obviously, that's a big problem which has to be addressed. One way to avoid overfitting is through early stopping. What is this early stopping? On x-axis, you'll have epochs, and on y-axis, you'll have accuracy values. As and how you keep increasing the number of epochs, usually what happens is your training data accuracy will keep on increasing. It will keep on increasing. It will keep on increasing that way. And what happens to your test accuracy is that the test accuracy values will keep on decreasing. It will keep on decreasing. It will keep on decreasing in that way. The point where the divergence or training accuracy and test accuracy starts diverging in a big way, you stop at that point of time and you call it as early stopping. Okay, but is there any defined criteria or how do I monitor this? Of course, there are a lot of things that exist which will help you do the early stopping. But then before that, when to stop? You might say that, hey, I'll train for 20 epochs, or maybe I'll train for 100 epochs, and then I'm going to reduce the learning rate and then train for another 20 epochs, and then I'll stop after 120 epochs. You can give this kind of condition also. And then you have this error change criterion. What do you mean by error change criterion? You stop when the error is not dropping over a window of 10 epochs. That is, you train for a fixed number of epochs after criterion is reached. Okay, let me explain. So, okay, I'll have this weight change. Okay, error change. You ran your model for epoch 1, and let me rather show it practically here. We have already done it, right? Yeah, all these epochs, right? So you stop when the error is not dropping beyond a specific percentage. For example, you started and you're calculating your accuracy. Okay. Uh, 1 minus accuracy is error, you know that. Or accuracy plus error is equal to 1. And you have all these accuracy values. Okay. If the accuracy value doesn't change beyond a point, for example, here you might feel that, do you know what, after 0.98 the reduction is, or the improvement is maybe 0.005, and then you can put a condition saying that if the error change is less than 0.005, then stop your algorithm. If the error change is greater than 0.005, only then proceed further with the next set of epochs. Otherwise stop. Doesn't make sense, right? Is it worth the investment? Is it worth running for more time just for that fraction improvement? Is a call that we take. Okay. What should be that criterion that you want to give is left up to you once again. It's left to the discretion of artificial intelligence expert, AI expert. So you take a call on what error change value really makes sense. That is error change criterion. Then what you do is you put a window, basically set 10 epochs. You will not say that from one epoch to another error change should be so much. You give conditions such as 10 epochs, 5 epochs, 20 epochs, in that way. If you have, say, 20 epochs, or say you put a condition saying that I'm going to say that my algorithm will stop if the error is not reducing by more than 5% in next 5 epochs. That means you monitor for 5 epochs, basically, like 6, 7, 8, 9, 10, 5 epochs. You look at this, okay? It's 0.9122. This. So let me take this. It's 0.9596. And here it is 0.9122. Is the change in the percentage more than 5% or not? If it's more than 5%, you continue. If it is less than 5%, stop. This is one way of applying your error change criterion. Here there is a variant of that. Variant is that train your model for fixed number of epochs after the criteria is reached. So what you do is, say your error is not reducing by more than 5% in 10 epochs. So epoch number 1 until epoch number 10. The change is not more than 5%. So what do you do is, rather than doing a hard stop at this point of time, you'll say that, okay, let me run for 1, 2, 3 epochs, 3 more epochs, by reducing the learning rate. So until now here, the new weight is equal to old weight plus eta value into error into input. Okay. Now Say you have used eta value of 0.01 for these 10 epochs. Now what you do is you change this eta value, lower it further to 0.001, and then try for another 2 or 3 or 4 epochs and see whether there is any drop in the error or not. If not, then stop. Why do you even need to do this? Might be a question. So what happens sometimes is your error surface might look like this. So maybe you reach the bottom, maybe here 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You're here. Okay, and then maybe if you can push slightly further, you'll go to the deepest of the valley. For that, you try for 1, 2, 3 epochs, and the moment the error change increases, it will go down the valley and reach the bottom. You'll reach the better valley, better minima, better local minima. Okay, this is what people do practically. Okay, we should not be too much of theory oriented, right? Practically, this is what happens. These are all practical examples. Okay, then weight change criterion. What is your ultimate objective? Your ultimate objective is to, your objective function is to minimize the error by changing the weights. And say this is how your error surface or whatever be it. Now you go with epoch 1, and if you have say 3 inputs, how will your network look like? 1, 2, 3. Say you have one hidden layer with 0 neurons, it'll be like this. Okay, say you have 3 inputs. Okay, 3 inputs. So fine. Forget about inputs. Let's look at weights. Weight 1, 2, 3, 4, 5, 6, 7, 8, and then you'll have a bias 9, 10. You'll have 10 weights. So you take all those 10, right? So bias and all those weights, W1, W2, all those weights, right? And make a note of these and call this as epoch. And let me do this. I'll get back to this. Epoch 2, epoch 3, epoch 4 in that way. Say you're at the current epoch number 10, which is called as epoch T. Current epoch is epoch number 10. The previous epoch will be T minus 1, T minus 2, T minus 3, T minus 4, T minus 5, T minus 1. In that way, this will become E T minus 10. Means from the current time period, I'm going back by 10 epochs. Okay, so take these weights also. Every epoch, right? Epoch is what once your entire training data set is traversed to your network and you come back and update your weights. That's one epoch. Epoch after epoch, weights will get updated, and say you have a final epoch. And you have all the weights corresponding to T, and you have all the weights corresponding to T minus 10. Look at each and every weight. Look at this weight and subtract this. So BT minus B, T minus 10. Is the difference less than maybe 0.005? You put some condition. This is also user defined. There's no thumb rule as such. Then subtract W1 and W1. Is the change in weight less than certain percentage? Right? Do this. W2, W2, W3, W3. Subtract all of those and keep calculating the difference. Take the maximum of those differences. So say if you subtract these two, B and B, say you got a value which is maybe 0.1. If you subtract W1 and W2, maybe it is 0.0008, so on and so forth. out of all these different values, even if a single value, is greater than this threshold that you have set, your training will continue. You'll not stop. When would you stop? You would stop only when, among all the differences, or all the differences basically, if it is less than the defined threshold, only then it stops. Otherwise, it doesn't stop. This is yet another criterion, weight change criterion, which exists. Okay. Then there is another thing which is very heavily used, which is called as dropout. Okay, what is this dropout basically, and how does it help? All these are, techniques to avoid overfitting. One is stopping criterion. You have error criterion and weight change criterion, and then you also have this dropout. What is dropout? Okay, and how does it help? So here, if you have a network which is fully connected, it is called as dense network. You all know that. Let me put it this way. Say you have a network in this way, 5, 4, 4, and then you stop. Every neuron will be connected to every other neuron in this way. Dropout, you put a condition saying that dropout is equal to, say, 0.5. What does that mean? 0.5 means when you pass each of your training example through your network, x1, x2, x3, x4, x5, and say you have also have an output variable y, and you have, okay, 100,000 examples. So when you pass each row through your network, okay, you drop randomly 50% of neurons. So you randomly choose 50% of neurons from this, 50% of neurons from the hidden layers. Okay, randomly drop 50% of inputs also. Okay, and then process it. Of course, you might ask me, hey, what is 50% of 5? 2.5. How do it? You round it off basically. You make it 3. Your algorithm will make it 3 and then proceed further. So randomly 3 are missed out. Randomly 2 from here, 2 from here are missed out. When you apply a dropout of 0.5. When you pass the next row, another random number, random 50% of the nodes or neurons will be dropped off. When you pass the next next row, again randomly 50% are dropped off. So random 50% are dropped off basically. This is something like this. Say ISRO is planning for a human mission, human on moon, right? For example, that's the mission, say ISRO is venturing into. When ISRO is venturing into this, and when they bring in people, say they brought in 1,000 people to work on this, what happens is, if you have different departments and everyone specialized in each of the departments, if a few people from a department resign, it's going to be a huge blow. Hence, I mean, this is a strategy which people also implement in a few companies. It worked well for them. So what you can do is you can say work should not start by 2022. I want to place humans on moon. So deadline is the same, but then you'll say that every day randomly 50% of people will take a leave. Randomly 50% of people take leave every day. So random 500 people will come. Who are those random 500 people who will come to work? We really don't know. That means, and work should not stop. That's the condition. So what will happen is eventually these 500 people will start working on all the work of the 500 people who are on leave. The next day, another 500 people randomly come. So these people also should learn the work of another 500 people who haven't come, because work should continue and launch date is fixed. This way, what happens is you are making everyone learn everything else in a generic manner. So you want everyone to learn everything else in a generic manner, basically. You're not making any specialized departments. You can otherwise say designing team, modeling team, construction team, testing team, in that way. That's being very specialized. But here, we're not letting things be specialized. We are making it very generic. So everyone learns everything else. That's the objective of dropout. Okay. Otherwise, what happens is a group of people will overtrain themselves, overtrain on the designing aspects. You don't want that overtraining to happen. That's called as overfitting, over dependency. You're trying to, in some sense, reduce that by making everyone else capable of handling everything else. Right? Very simple. That's your dropout. And in this way, there are a lot of other techniques, but then in the interest of time, we will move on. Okay. One more thing which I need to explain is batch norm, batch normalization. I'm going to explain those things which are very heavily used, okay, rather than looking into each of the aspects. And dropout is one thing which is heavily used, which is a regularization technique which is used to avoid overfitting. We also have something called as batch normalization. What is batch normalization and how does it work? What happens in batch normalization is, say you have 10,000 samples, one, two, three, in that way. Say you have 10,000 samples. And say you have a batch size, which is equal to 1,000. And here you create different batches, right? Say in that case, how many batches would you have? 10 batches. 1 to 1,000 will be one batch. 1,001 until 2,000 will be second batch. 2,001 until 3,000 will be the third batch. And then 3,001 until 4,000 will be another batch, so on and so forth. You'll have all these batches. Okay, you have multiple batches. Out of these multiple batches, you take each and every batch and you have a network, assume like this. Every neuron is connected to every other neuron. Okay. And after you pass the entire batch through your network once, you come back and update your weights. That's called as one iteration. One iteration. Then you take the next set of 1,000 entries, pass it through your network, go forward, calculate the loss, come back and update the weights. That's called as one iteration. This is called another iteration. So you completed two iterations in this way. After each iteration, that is after each batch, you try to normalize the weights. Whatever weights you have, you try to normalize. You take all the weights. Say you have 1, 2, 3, 4, 5, 6, 7, 8, and then you'll have one bias, that's 9 weight number. You'll have another bias here, weight 10. So you have 10 weights, right? You take all those 10 weights. Take all those 10 weights and do what? Calculate the mean of that. Calculate the standard deviation of that. And then apply the formula. New weights, new weight is equal to old weight minus mean divided by standard deviation. When you do this, new weight is equal to old weight minus mean divided by standard deviation. When you do that, you're normalizing your data or standardizing your data. After every batch, do that normalization again. And hence it's called as batch normalization. The advantage here is that when you have your error surface, the training will become faster and you'll reach the bottom faster. Bottom of the error surface faster. Okay, that's the advantage of doing a batch norm. The third thing is data augmentation. When you have images that you're dealing with, do not think twice. Just apply data augmentation or video analytics, right? Video is nothing but combination of multiple images. Videos are nothing but combination of multiple images. Take each image, each frame is called as each image. You take each frame and do certain augmentation. For example, change the color, add red color or green color or blue color, right? Swap the positions, rotate the image, zoom the image. There are bunch of techniques which exist. And what ultimately happens is the amount of data that you have would become humongous. And for the cancer project that we have dealt with, initially when we started off, we had only approximately 3,000 mammography images. We had only 3,000 images, mammography images. With 3,000 images, you obviously cannot train your network. So the underlying question is, what do we do? We have less image. Either go ask the customer for more. Customer would obviously say, this is all I have. Then what do? Augmentation. What we have done is we have rotated the images. If you have an image on this, you flip the image. You rotate the image, maybe 20 degrees clockwise, 20 degrees anti-clockwise, 30 degrees clockwise, 30 degrees anti-clockwise. And you flip your image colors. And you do a lot of transformations. Okay, you do a lot of transformations. Basically, when you do a lot of transformations, things will fall in line. Okay, this is how you improve the model performance. And finally, after this, we will take a break. Weight initialization is very, very important. One way is to randomly initialize the weights, and by default, people use random initialization because there are a lot of techniques such as Xavier's, Cafe's, He's initialization, etc. But these initialization techniques are not extremely beneficial than randomly initializing your weight. So what happens is, say you want to initialize the weight for this node here, these two. So what you do is you look at fan in, means how many inputs you're getting. 1, 2, 3, 4. 4 inputs. So it'll be simply put square root of minus square root of 6 by square root of fan in is 1, 2, 3, 4 plus fan out. How many are coming out? 2, comma square root of 6 by square root of fan in, fan out. So it's nothing but minus 1 to plus 1 because this is square root of 6 by square root of 6. So you get minus 1 to 1. In the range of minus 1 to 1, you pick up the values, and picking up any value is equally likely. So all these weights that will be initialized here would be in the range of minus 1 to plus 1. And you have a variant of that, 2 by fan in, 4 by fan in plus fan out. Okay, that is also a possibility, but majorly people go with this. Okay, quickly, a few things. Stochastic gradient descent, when I say SGD, it's mini batch SGD. Okay, it's something that you can use, or you can use Adam, Adagrad, Ada Delta, all these advanced things basically. Again, these are explained in a very detailed manner as part of our full-blown AI training. I repeat, 80 hours versus 20 hours, there is a difference. Okay, ReLU families are amazing. You have ReLU, Leaky ReLU, ELU is also very good for your activation functions. That is the hidden layer activation functions. Batch normalization and dropout happen to be excellent regularization techniques. And if you're dealing with images, data augmentation is the best way out when it comes to vision related applications. We have 3 days left, right? 3.5 basically, right? 1 more hour left. We'll get started with computer vision, and weight initialization is a very important thing. But do you know what? Whatever be it, I personally have not experienced anything which is better than random initialization. So I let my model randomly initialize the weights. Sometimes I go with Xavier's just out of my curiosity on how it works. Sometimes it works well, better than random, sometimes not. Okay. So this is how we are planned. You know, we will take a break now. After break, we will look into computer vision. We'll not get into core depth of it, but at least to some extent, I'm going to explain you guys. And then tomorrow also, first half, we will do this. Then we will switch to CNN, convolution neural network, which will go on for one whole day. I can say that entire 27th would be for this. And 28th, I'll put it this way, 25th, second half now, and 26th probably will spend on computer vision. CNN would be on 27th, and RNN and its variants would be on 28th. This is how we have planned the schedule. All right. So please take a break for 10 minutes, 6:05 to 6:15, 10 minutes break. And post break, we will get started with computer vision. So please ensure that you come back. And a lot of people are curious to learn on how to analyze images. So please be back, friends. Let me mute, and yeah, please come back after the break. Okay, let's continue. I'm assuming that our team is responding to you. Okay. Yeah, it is applicable to input layer and output layer neurons. Show me all updated weights in each bar. Yeah, that is a different way. You don't know all that. You can save the model. Those are all advanced things, Venkatramana. Actually, it's taught as part of our full-blown training. Here, it'll be a little difficult. Okay, if you have less data other than images, how can we proceed? Then you can add. You have to get more data. Simple. You mask your data and simulate your data otherwise. So what usually happens is there is something called as data simulation. You might want to explore this. Data simulation is a technique which is used to get more data. Say you have only 1,000 data points. What people usually do is they look at what is the underlying data distribution. If it's normally distributed, for example, then you'll have data which is normally distributed with mean mu and standard deviation sigma. Okay, and then you say that with this mean and with this sigma, generate another 100,000 records in that way, and then it will generate for you. But generated data is generated data. It won't actually be closer to the actual data, right? Aparna, hope that answers your question. And Sujana answered your question. Okay, next. Thing that we need to look into is computer vision. But our team would be responding behind the scenes. Yeah. If they are not responding to your queries, what you can do is you can just log in anytime between 12 p.m. to 5 p.m. Log into our YouTube channel and there'll be YouTube live happening. You post your question there specifically and we will absolutely clarify. Yeah. All right. Let's move on further. So let's understand about computer vision and image processing, wherein I would skip the initial part, which is all basics. I would actually want to get into the core depth of it, given the limitations, right? So let's proceed further. What do you mean by image? Anything on which light or some kind of energy falls would reflect something else, and because of that, you're able to see the image, and the image that you have is broken down into pixels. And when you have a grayscale image, the pixel intensity values range from 0 to 255. 0 means black, 255 means white. And here you have all white, 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 right? So it's all 255. Here you have complete black, so that's given a number 0. This is not extremely black, but it's very close to being called as complete jet black. That's 20 number. And in this way, you have a lot of other values. So you have 0 for black, 255 for white. Then an image can be represented as a function. Any image can be represented as basically a function. And if you look at this Arnold Schwarzenegger image, it appears as if it's a function, right? And if you closely observe here, you have x-axis and you'll have y-axis And for each and every pixel, so say if you say x equal to 1, y equal to 1, that's probably the first pixel, so on and so forth. For each and every pixel, you'll have pixel intensity values, which is represented using f of x comma y. This is nothing but intensity values. These are pixel intensity values. If you look at this line here throughout, it is black, 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 black throughout. So it is all hollow over there, right? Shallow. Because here you'll have 0 and here you'll have 255. And the pixel intensity values range from 0 to 255. 255 means white color. So in this way you go here and here you have all white color is 255. And then from here you have black. So if you observe here, it's all black. So it's at the bottom there. And 255 is white. So you see a white color. Even if you have a color image, color images are represented using different colors. And here, even if you have a color image, if you delineate the different color channels, like this is an RGB color image. If you delineate the red color, green color, and the blue color, you'll get the red channel, green channel, and the blue channel. The three color channels. And when you look at each individual color channel, it appears as if it is of grayscale. It appears as if it's a grayscale image. There are a few image transformations. Question to you all. If this is the output image, g of xy, and f of x comma y, if this is your input image, that means x comma y means you have x and you have y. For each and every value, if you consider each and every value, and if you each and every value means each pixel value, and then if you add 20 to it, what do you think will happen? Yeah, please can you all respond? What do you think will happen if I keep adding 20 to each and every pixel value? I take this pixel value at 20, I take this pixel value, this. For each and every pixel value, I keep adding a number 20. Then what would happen to the output image? Yep. Please, can you answer? Let me see on what responses we are getting here. Absolutely. You can add any number. I've given just an example, Kiran. Just an example to learn the concept. We have to learn concepts, right, Kiran? So we are learning the concepts. As part of that, I gave one example. If we add 20, what happens? I'm just explaining you image transformations. Yep, exactly. A lot of y'all are getting it right. Right? So, you know for a fact that pixel intensity values range from 0 to 255. 0 means black. Say you have a value or a pixel intensity value here. If this is 0, and if I add 20 to it, what will happen? It will start moving towards the brighter side. 0 means black, 255 means white. So it will, if you keep on adding 20, it will keep moving towards the brighter side, white side. Another question: if already there is a pixel which is completely white, for example, if this is 255, and if you add 20 to it, then should the output image have a pixel intensity value 275? Does that exist? I'm saying the maximum pixel intensity value will be 255. So what do you think will happen in this scenario? It will force fit any number greater than 255 to 255. Okay, it's going to force fit. So our image here has become white. Okay, next. If I take an image, here you have X and Y. Okay, I'll also give you a hint. If you have X and Y in this way, this is origin 0, 0, and you have X equal to 1, 2, 3, 4, 5, 6 in that way. And you have Y 1, 2, 3, 4, 5 in that way. And you have -1, -2, -3, -4, -5 in that way. Here also you'll have negative values. Okay, now if I change all the X values to -X, then what do you think will happen to the output image? Yeah. Any thoughts, anyone? What do you think will happen to the output image? Let's see. Let me look at your responses. Mirror, exactly. You're going to flip the image, right? The images get flipped. Wonderful. So if you put this image here and you're saying each X value, I'm going to make minus of that. So if the X value is 1, it'll become -1. If X value is 2, it becomes -2. If X is 3, it becomes -3. X is 4, it becomes -4. Then what happens is this image will get flipped onto this side. There you go. Image is getting flipped. Absolutely. Mirror image is what you'll see. Okay. And this is fine. Now, I'm just skipping a few just to ensure that I get into the core of it, just to explain you all. Okay. In that way, whenever you have an input image, you can apply some operation on that input image to get an output. So if you're taking a 3x3 window in this way, and if you simply take average of all those values, you get 0, right? So here what we are doing is, though we want the value of this central pixel, you're taking the neighborhood of that, around that, and you're taking a window size of 3x3. And what we are doing is, you're taking an average of all those, and you're getting an output image here for this pixel. Now if I move it by one stride, this is called as moving by one stride. That means by one pixel towards the side. When you take all these values and when you take average of all those values, you get this central pixel. What is that turning out to be? 10. Then you move it by another stride. Then take all these values, take an average of that, and then you get the value of the central pixel, which is here. If you keep moving your window 1 pixel at a time, 1 pixel at a time, 1 pixel at a time, then you get an output image like this. Why are we doing this? I'll explain. I'll get there. That's one way of applying. Just this is called as filter. This 3 by 3 window that you're seeing is called as a filter, or a kernel, or a mask. All mean the same. Kernel or mask or filter mean the same. So you take your input image and say you're applying a kernel or a mask on it, or filter, and then you get the output. How? Here, let's see. In this scenario, what we have done is we have simply taken average of all the numbers. But that need not be the case always. You might have some numbers in this. And if you say 0 into this, plus 0 into this, plus 0 into this, plus 0 into this, plus 0.5 into this, plus 0 into this. So if you do that multiplication, you get the central pixel, which happens to be 8. You solve and see. Only everything else is zeros. Only these three are non-zeros. So 0.5 into 6 will be 3, plus 1 into 1 will be 1, plus 0.5 into 8 will be 4. So when you add them up, you get 8. Okay, next. I think this should be here. Okay, let me ask you this question. Okay, forgot about the bottom thing. How do I do? What do I do? Let me maybe use a different color. Which one should I use? Let me use this. Let me use pink. Take the pink window as a reference. Okay, there's something wrong with this. And tell me on what should be the values of this kernel or filter or mask such that this central pixel value turns out to be 30. Yep. Please let me know. Please try. You will be able to get it. What should be the values inside this filter such that when I apply this on this patch, pink color patch, the central pixel value turns out to be 30. Let me see how many of y'all are getting it right. Oh, you get okay. You are yet to try. Okay, that's okay. Let's take quick minute, and let me know, friends. Again, I repeat the question. What should be the values within this filter such that if I apply this filter on this pink patch, the central pixel value turns out to be 30. Let me see now. Do we have any responses? Wonderful. Wonderful. A few of y'all are answering it. I really appreciate it. Yep. So, do you know what? If I have all 1 values here, okay, then what happens? 1 into 0 plus 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 1 into 90 will be 90 plus 1 into 90 will be 90 plus 1 into 90 will be 90, which should be 270, right? 270 divided by 9 will give you 30. So that means I should have 1 by 9 here. Actually, yes. So the condition for this kind of a filter that you're seeing, which is called as linear filter, the condition is that when you add all these numbers, the numbers should add up to 1. But here, when you add all these numbers, it turns out to be 9. And what is 9 by 9? 1. So that's why you're dividing. In short, 1 divided by summation of all these numbers should be there in that way. Next. What will happen if I apply such a filter? Might be a question, obvious question. If you take your original input and if you apply a filter, which is like this, if you have all numbers same, right, like 1 1 1 1 1 1 1 1 1, and when you add all these numbers, you'll get 1 by 9. Okay, so if you apply this kind of a filter on an image, the resultant will appear like this, the output. So this is your input image and you have an output image. And this output image that you're seeing is called as smoothened image. Hence, this filter is also called as smoothing filter or smoothing filter or a box filter. Okay, box filter or smoothing filter, which will actually smoothen your image. And you know what? If you keep increasing the size of the filter from say 3 by 3 to 5 by 5, what happens is your amount of filter or amount of smoothing increases. Okay, amount of filter or amount of smoothing increases basically. And the disadvantage, one disadvantage here is that you see that boxiness on the image. If you observe, you'll see that boxiness, right? You'll observe that boxiness basically. That boxiness can be countered using Gaussian filter. Oops, sorry. I just spilled over some water. Sorry. Okay. So here you have Gaussian filter. What happens in a Gaussian filter is that the pixel values which are at the center will have high weightage. The pixel values which are immediate neighbors will have slightly low weightage. And the pixel values which are diagonally opposite will have even less weightage. But then the rule holds true. Summation of all these values should turn out to be 1. When will the summation of all these values will turn out to be 1? When you add all these numbers, if you're getting 16, you just divide it by 16. When you do this, the rule holds true that when you add up all these numbers, addition will turn out to be 1. And when you apply a Gaussian filter, say this is your input image, when you apply a box filter or an average filter, both mean the same, on an image, You see those boxiness, but the moment you apply a Gaussian filter, that boxiness is gone. You have to carefully observe those boxes, kind of this shape will be there inside, small boxes like checks. And here that issue does not arise. And the amount of smoothing on your image, say this is your image, if you apply a Gaussian filter which has small variance, so Gaussian means normal distribution basically. If it's like this, the variation is less. So amount of Gaussian is less. If the variation is large, then the blur is more. If the amount of blur is even large, okay, if the amount of blur is even large, I mean, if the variation is large, the amount of blur will be too much. So you decide on how much of blur is actually needed. It has a lot of applications on Adobe Photoshop, Picasso, so on and so forth. Okay, next. If I take this image and apply it on this filter, what do you think will be the output? Yep, please go for it, friend. I mean, you might go wrong, that's okay, but if you're not trying, you're actually losing very early. Okay, let me see. Look at your responses. Same, wonderful. A lot of y'all are getting it right. That's awesome. That's awesome, truly awesome. So if I apply this, what happens is, if you take on this, if you apply on this patch, what happens? All these neighboring pixels will be zeros, right? 0 into this, plus 0 into this, plus 0 into this, plus 0 into this, plus 0 into this, 0 into this, 0 into this, 0 into this. Only pixel value that gets multiplied and you'll get an answer is for the central pixel, which is getting multiplied by 1. And that would be your output. That means the same value will appear here. And when you move it by 1 pixel in this way, again, only the central pixel will get multiplied by 1 and the same pixel value will come here. If you're multiplying something with 1, you'll get the same thing. Okay, and that's the same thing. When you take your original image, apply a filter, you get an output which happens to be the same. If you apply a box filter, what do you think will be the output of the image? How do you think the output of the image looks like? Yep. What do you think will be the output of the image? Go for it. I'm sure you'll get it right. Absolutely. Absolutely. A lot of y'all are getting it right. It will actually blur the image. It will actually blur the image in this way. Wonderful, right? So a lot of filters is what we have discussed. Now what I wish to do is, I want to take you guys to some amount of programming, because I think we are doing theory, that's good, but then let's also practically deal with that. So I will click on the eraser and remove everything. And where is this? It's here. Let me go to, where is computer vision? It's not here. Oh, open CV. It's here. All right. There's a lot of code, a lot of things that we need to do, but again, we will restrict to certain aspects. CV2 is computer vision, and we are going to make use of open CV, open computer vision. And using open computer vision, we shall proceed further. How do you install this? To install this, you need to go to, where am I? Where am I? Where am I? Here. Yeah. Go to environment. Okay. And then do a drop down. Click on open terminal, and you need to type pip install OpenCV and click on hyphen Python. Sorry, for Python. OpenCV can be installed on a few other softwares also, but we are going to install this OpenCV on Python. When you click on enter, it is going to install. I've already installed it, so we need not rerun that. I'm just showing you this so that you don't struggle when you practice. So you import CV2. No module name. Wonderful. Let me go here and check on whether we have OpenCV or not. But I think that's not needed. I should have, let me cancel it. Messed up big time, huh? So Windows will be Windows. In real world, practical world, when we do projects, we prefer Linux, friends. We work on Linux. Windows, oh my God, is super crazy. Look at that now. It for no reason stop this. Okay, let me do one thing. Me close this. I think that's the only way out for me to get rid of it. Let me relaunch Anaconda. And it's coming up. Come on. Yeah. So I would launch this spider. So it's launching. Let me open a new thing. Okay. Control L. Okay. I don't want to see the history. Okay. Now I would go here to environment. I will do a drop down, click on open terminal, and I will say pip install opencv-python. Enter. Wonderful. It's going on. Okay. So you say import CV2, and then you do this cv2.imageRead. You want to read this image, which is in C drive. Okay, mandrel.tif. and then you're assigning it to an object called image. You have the image here. And you know what? Let me show this image to you. Copy this, go here, and let me post it here. This is the image, guys. This image got converted into pixels. If you see here, it's a color image which is of 256 by 256. That means you have 256 pixels along width and 256 pixels along length. And then you have three color channels, R, G, and B. Red channel, green channel, and blue channel. And you have the pixel intensity values. And when you say cv2.image show, image show, im means image show, and you're saying you want the window name to be input image, and you want the image. What image do you want to see? This image, manual image. And the cv2.wait key of 0 means, wait key means wait for these many milliseconds before you close the window. Sometimes people accidentally close the window. And if you put say 100 here, for instance, until 100 milliseconds, you cannot close that window. It'll be open. Okay, that is what it means. When you say 0, that means you're saying, I need not even wait for 1 millisecond. If you want to close it. That is what it means. And let me run this. So here, there's a window. I'm sure this is not the window. This is just a photo. I think I have to close a few of these things so that it appears. Sorry, close a few of these windows. Yeah, here it is. Okay, let me close whatever I should actually close. Yeah, here we go. So this is the input image basically. You are able to read it. If I press an escape key, this will go away. Then say you want to read that image, which is in color format, and you're saying you want to read that image in a grayscale format. Interesting. So if it's a color image, and if I say cv2.image read in grayscale format, would it actually open the grayscale image? Oh yes, let me run that. And look at this gray image. That's the name of the object, gray image. So gray image. 256 rows and 256 columns. And then you have three color channels. Here you don't have any color channels, so it is grayscale image. Okay, so if you run this, it's here, grayscale image. Look at that. Wonderful. So it automatically converted it into grayscale image, basically. And I press on escape key and I can actually close this. Now, cv2.image write. Oh, can I also write it? Oh, yes, absolutely. You can actually save it. So you're taking this grayscale image. You first of all took a color image. You imported that into, while you imported, you converted that into grayscale. And then you're writing that image in a grayscale format onto your computer, and you're naming it as output.tif. Like you have JPG format and all that, you have TIF format. You're writing it. And then what you're doing is you're saying import OS and os.get current working directory. To do that, you get this. If you go to this path and check, that image would be saved. You will find the saved image. Let me go here, C drive, users, Bharani. And yep, today at 6:55, this got saved as output. Oh yeah, grayscale image got saved. Many things is what you can do. Let me show you this. Wherein what we can do is you actually take that image, this color image, okay, and what you're doing is you're saying convert the color from BGR to YUV. Okay, you can split it ideally into a color space which is called as YUV. There are different color spaces. Most widely used is RGB color space, red, green, and blue. You also have YUV format, HSV format, a lot of formats. Of course, a little bit of depth would be there as part of our uh, main program, but then, sorry, I keep saying that not to request you to join, but then just to tell you that, that's the reason why I'm not getting into the thorough depth, because of lack of time, or given the time constraints, we are trying to do the best. That's the only purpose. Okay, so you're taking this color image, converting that into a different color space, then you're splitting the color space. You're splitting Y channel, U channel, and V channel, and then you can actually view all those color channels: Y channel, U channel, and V channel. Let's see. Wow, wonderful, isn't it? You have the Y channel, U channel, and V channel. Do you know what? This is your original image basically. So color image got split into Y, U, and V. As I've told you, color image, when you split it, it appears as if it's a grayscale image. And you can combine this. All these are kind of data augmentation techniques when you deal with cancer prediction model, or cancer images, or lung images, or any images basically. A lot of such applications exist. Your Adobe Photoshop, when you open and look at it, all are, these kind of applications is what you see to a very great extent. So I'll stop here. And tomorrow when we connect, we are going to take this discussion further on images. So where are we? Yep. So the attendance link is posted. You might want to just give the attendance and take it forward. One more thing I wish to tell you, that when you go to our YouTube channel, okay, the best part is that from 12 p.m. to 5 p.m. you can ask your students, you can ask the other faculty members, or you yourself. You just log in and you can ask any questions that you have. Yeah, but please do not forget, I request you to ask your students and other people to subscribe and click on this notification. Thank you so much. We'll be posting the quiz on our LinkedIn and Facebook. Yeah, sure, let me copy this and yeah, here is YouTube channel. We'll also post a message wherein YouTube channel details also would be there. LMS already we started sending it, Raghuveer. In the next 1 or 2 days, you'll be receiving it. We already started communicating, Raghuveer. Whoever has registered with us, we have started communicating, sending out LMS details. Answers to the quizzes are not given, Kranti. It's just crowdsourcing, meaning you yourself can find out. Those are all very simple things. But then it will be a very good exercise for you all, right? Okay. Anything else? Sure. No problem. Yeah, net issues might be there. All right. Thank you so much. We would connect again tomorrow and take this discussion forward. Thank you all. Bye.